Right, so we filled in the DP table for our house robber question and it said the maximum value is 19. And as we are very familiar now, any dynamic programming question will only give you the maximum or minimum value. To find the actual configuration of parameters or variables, we have to do something called backtracking, which again is exactly what we will do here. And what are we going to find out by backtracking? Which houses were robbed and which houses were not robbed. So basically, if we find out which houses were robbed, that is enough. So that's what we're going to try to do in this backtracking process. And because we saw that this question is very similar to your coin change problem in terms of filling the DP table, we will also use a backtracking logic which is very similar to the coin change problem, because in both cases the idea was to pick or not to pick an element. So if you have picked a specific element, then that grid and its immediate predecessor grid will have different values. If you have not picked that element, that grid and its predecessor grid will have the same value. So this is what we saw in coin change as well, and that's exactly what's happening here. In fact, here it becomes simpler because unlike your coin change, the table is one dimensional here. So as usual, you'll start with the last grid, which is where you get your answer. You see that if you rob house number 6, some combination of houses up to number 6, your maximum value is 19. Whereas if you rob some combination of houses up to number 5, the maximum is only 15, which means we have robbed house number 6. So DP of 6 is not equal to DP of 5, which means house 6 was robbed. So you include number 6 in your robbed. Robbed is the list of houses. And now that you know number 6 was robbed, you know because of the non-adjacency constraint, 5 could not have been robbed. So you skip 5 and you jump directly to 4. Now you see DP of 4 and DP of 3, again 15 and 10 are not equal, meaning house number 4 was robbed. So again you add 4 also to your list. So now because 4 was robbed, 3 could not have been robbed. So you jump from 4 straight away to 2. Now here you see that number 2 also the value is 7. For number 1 also the value is 7. Meaning house number 2 was not robbed. So you will move one step further. You will go to house number 1. Again you will check this is a 7, this is a 6. Meaning this was robbed. So you will put 6, 4, 1. You know that 1 has been robbed, so 0 could not have been robbed. You jump to the previous one, which is the base case, and once you reach the base case, your backtracking stops. So to summarize how the backtracking happens, you will start from the last grid. You will check DP of I and DP of I minus 1. If they are unequal, it means the ith house was robbed. So you will add I to the list of houses which was robbed, and then you will jump straight away to I minus 2 because of the non-adjacency constraint. Whereas if DP of I and DP of I minus 1 are equal, then ith house was not robbed. So you go to I minus 1 and you continue the comparison. So you keep repeating this until you reach the base case, no house robbed. And finally you will have this list. So the robbed houses according to this example were 1, 4 and 6. And the total value should be val 1 plus val 4 plus val 6, which if you go back to this array will be 7, 8 and 4. 7 plus 8 plus 4, which is 19, which is exactly the answer we got. So that is the house robber problem.